Good afternoon. I'm Jeremy Mikola. This is using MongoDB responsibly. Thank you for showing up to this sweaty room. So just a little introduction. I previously am a core contributor for Symfony. Previously worked at OpenSky and exercise.com. So I have inside knowledge of the early way of doing things wrong with Symfony 2. And as of 3 weeks ago, I started a position at Tengen on the PHP driver team. Not developing C driver code yet, but mostly going to be working on Doctrine ODM and then moving on to the C driver as I pick up some knowledge. So if ODM doesn't work for you, you can complain to me, and I'll complain to John Wage for you. So there's a medley of topics that I'd like to cover today. Hopefully we get through everything and then have some time for questions at the end. So the main points are talk about different infrastructure of using MongoDB, aspects of concurrency, which is something that's been recently improving in the last 2 versions of the database. We're going to go over indexing, which is important in any database that you're using, as well as walk through query optimization, some general tips from the last bunch of projects that I've been working with over the last 2 years, and then a case study of refactoring a bundle, doing some schema optimization. And then we're going to talk about MapReduce and aggregation framework, which probably not many people have used because it's not stable yet. Hopefully the 2.2 release should be released within the next month or a half or so. And then talk a little bit about Doctrine ODM, but mostly going to be focusing on Mongo itself. And then a little bit about Mongo monitoring service from MMS, which is a free statistics service that Tengen provides to track your Mongo setups. So just a show of hands is who has used Mongo, and how many people are here with no knowledge of Mongo at all? Okay, the entire Doctrine team has no knowledge of Mongo. So it's very disconcerting. So the first, to just go over the infrastructure, or the people that are not familiar with Mongo, a NoSQL database, so there's no fixed row and column schema. Essentially, from the developer's point of view, you can be ignorant and not forget about the ops people for now. You could just store JSON and get JSON back. And then underneath, there's aspects of replication and sharding are probably a lot easier than they would be with SQL. So that's its claim to fame. It's really flexible to work with, and especially if you're working at a startup and you have changing product requirements, your schema is going to change the next time the business guy has a different idea. And rather than having to migrate all your data over, you can just start inserting the data in the form that you need and clean up later. So the infrastructures that we're going to introduce first, this is actually what exercise.com for the last 2 years has been using. They're still using it as of last April, unless they change something. So this was a traditional master-slave, which really needs no explanation. But there's a better thing that we'll get to on the next slide. But basically, master is where all the writes are going, and then you have this slave that's replicating from the master. And if you send queries and you are comfortable getting the slave, it might be a little out of date. So if you add the slave OK bit to your queries, they can go right to the slave, and then you can get some extra performance that way. But it's really not for scalability. It's more for durability and data protection in case your master server goes down, you can step up. But the failover process is manual. So if master server does go down, you're going to have to call your ops guy or someone and make sure the slave gets promoted manually. Bring Mongo down, your site's going to go down. So this was what Mongo originally had. It's not ideal. And soon after, they came up with replica sets. And this is really what you'll want to use for data redundancy. So we have, in this case, we have a primary and a secondary, which are kind of analogous to master-slave. And you could still send your slave reads directly to the secondary server, which is read-only. And the benefit here is you have automatic failover. So if we take down the primary server, then I'll get to this in a minute, but the secondary is going to immediately step up to primary, and then maybe you have a hiccup for some connections get dropped, but once the driver is aware of the promotion, your writes will now be going to the secondary that was just promoted. And the purpose of the arbiter here is that when you have a replica set, you always want an odd number of voters to break ties. So if the primary was to go down, if it was just the primary and the secondary is going to say, I should be promoted. The primary has no vote because he's dead. And then who do we trust? So that's the point of the arbiter. It's just a process, holds no data. It just votes to break ties. So he tracks who's actually up and down. If we have an odd number of nodes in the replica set, we don't need an arbiter. And so this is actually what OpenSky is using currently. And exactly as before, except you don't need the extra arbiter process. And all these arrows going on here, basically, these are reads going back to the application, slave OK reads. We have read and write going to the primary, and then replication, which is happening behind the scenes. The secondaries are constantly trailing whatever operations are happening to the primary, and that's called the oplog. So they replicate that constantly, and then there's usually a small delay, which shouldn't be too serious of an issue. But usually they're a second or less behind. And then the grander infrastructure is sharding, and this is where you actually have to start scaling out. So now in this example, we have multiple replica sets. We have these MongoS daemons, which are really just routers, the same way you might have HA proxy in front of a web server. And they're going to have knowledge via the config servers, which are just storing very small configuration data. And for redundancy, there's 3 of those. There could either be 1 or 3. And basically, they're storing where the chunks of the shards are. You can shard at the collection level, which is collections are analogous to tables in SQL. And so you might have a users and a tweets collection that needs to be sharded, and they might be sharded on different keys. And you might have other collections like admin settings collection that doesn't need to be sharded. So that might live entirely on one replica set. And the MongoS nodes are going to know how to route any incoming queries. And if you're querying for something that's split across 3 different chunks, 3 different replica sets, the MongoS, say you're sorting across everything, you need to get all this data back. MongoS would dispatch accordingly and merge everything back to your application. So your application is really unaware that you're connecting to anything different than if you were just connecting to one replica set. It's a fairly transparent process. And the config servers are constantly replicating the state of where chunks live on the different replica sets. And basically, the MongoS really just has a cache of the configurations. The configurations are the authoritative source of where everything is. And this is exactly what I just discussed. So config servers are actually MongoDB processes, and they replicate separately, different process than a replica set. But it is replication between the 3 of them. And the main difference here is that sharding is what you're going to use to scale, and replication is for data safety, high availability, disaster recovery. So replication is probably not ideal for people who think, oh, I could scale out my reads. Ideally, no. There comes a point where you're going to have more writes, so there's certain operations that you can't run on your secondaries, and you're going to be hitting your master more frequently. And in practice, both OpenSky and Exercise are almost all their traffic goes to the masters anyway. In both cases, the replication is usually just for the data redundancy, and there might be a couple hand-picked queries that might target secondaries. But usually, the master is robust enough to handle the load of the traffic, and when you need to expand, then you shard. So moving on to how concurrency works in Mongo. So there's read locks and write locks, like typical databases, and these need to be yielded periodically to imitate some form of concurrency. So if we're having long-running read queries, every 100 documents that are being read, Mongo is going to release the read lock to see if there's anything else that takes priority. And practically, that might be a pending write, which needs to get through. And then also, if we have writes to many documents at once, the write locks will be periodically yielded for other writes to get in or other quick reads. As of 2.0, which hopefully most people are using, it's safe for production for a while now. There's yielding on page locks, page faults, which is basically whenever Mongo has to hit disk, and you'll hear this a lot, Mongo is fast because it works in memory. When it has to hit disk, you don't want to have to deal with it. So the solution here is that's going to take a while. We're waiting for spinning disks or just EBS volumes if you're on Amazon. So let's release the lock and we'll wait until our memory has been, the virtual memory has been populated from disk. So that was a huge performance impact. And then with respect to write locks, they always have priority over read locks. So if there is 5 read locks waiting to get access and a write lock is also there, he's going to be given access first. At a huge burn point of Mongo up until the last version was that there was a global lock in the database. So you could only write once at all. So now since 2.2, or if you're using the unstable 2.1 version, there's database level locks. And hopefully down the line there's going to be collection level locks. And this is all one of the prioritized features at 10gen in the coming 2-3 versions down the line is it's going to be keep adding more concurrency improvements. And that's really their goal for the immediate future of Mongo. So another, I guess, a selling point of Mongo being flexible to work with, you can use JavaScript as a first-class citizen, which maybe you can do in PostgreSQL as well. They have an add-on for it. But basically, your database shell, if you're connecting on the command line, is a JavaScript interpreter. And you can write, instead of writing stored procedures, you could write JavaScript functions. And then also, when you're running your queries, not this is advisable, but you can have a freely flexible where clause that inspects your documents using JavaScript. If you had some ridiculous comparison logic that could not be expressed in Mongo's query language, you could use a where query and find exactly what you need. There are several database commands which in the PHP driver you would execute through the driver as run command, but for the purpose of the presentation, I'm going to be using the terminology for the command line. So when you're in the command line in the shell, DB is always the current database that you're using, very similar to a SQL prompt. So DB eval is just you would give it a function and it would execute that JavaScript for you. And then JavaScript also comes into play with map-reduce queries. Your map functions, your reduce functions are going to be written in JavaScript. So currently, the default JavaScript interpreter in Mongo is SpiderMonkey, which I believe is Mozilla's JS interpreter. This is single-threaded, so all the JavaScript that executes in Mongo, you're basically executing one thread of JavaScript at a time. There's no concurrent JavaScript execution. There's a ticket which has been implemented to some degree, which may show up later down the road if you can compile Mongo with Google's V8 JavaScript interpreter, and that has support for multi-threading. It's not entirely stable, but it's something that would be an option if you really needed to research it. But in general, we're going to find out later in the slides that there's better things to use than running JavaScript directly in your queries and on the server. So just a little bit about DB eval. When you're running JavaScript on the server, this by default is going to take a write lock. The interpreter doesn't know what you're going to do with data. You have access to run other commands. You have access to read and do many updates within your JavaScript function. So it's going to take out a write lock for you by default. So since the JavaScript function is taking a write lock, you can't execute other things that would, other commands that would block, which isn't, you can do writing, but there's other actual database commands like ops operations, which aren't available to you. And one way that you would typically, this would not be a selling point, but one way you can use it to your advantage, if you have to do ops or admin operations, and you need to do something atomically on the database and ensure that nothing else is going to be writing at the time, you can do this using evaluated JavaScript, and it'll lock the database. A common example for this is there is no atomic swapping of collection names. You can rename collections, but you can't exchange names. So you can write some JavaScript that'll run both commands, and it'll basically execute atomically. And then also, if you have find and modify routines that need to run and they're complex, you need to do them atomically, you can use this. And then if there is JavaScript without blocking, you have the option to turn off locks as of a recent version. And the other advice is to use the Mongo command line client. So in that case, the JavaScript you run is going to be executed in the command client, not directly on the server as you would with a PHP driver. So when you execute JavaScript through PHP, you're basically sending code over to the database server, and it has to do the interpretation. If you're going to run JavaScript from your Mongo command line, the command line process will execute the JavaScript and execute those commands as actual database commands against Mongo. So basically, using the command line tool, you're using a JavaScript client to interact with Mongo. So that's, if you need to do a lot of JavaScript operation, that's probably a preferable way to do it. Is there a question? Yeah.
Is it to do for the driver, or is it just something that is going to be skipped? I mean, the PHP driver.
Oh, for the so all the drivers in any language, when you to do DB eval, most of the languages have a native representation of in PHP it would be Mongo code object, and it's a string, and it basically gets serialized as this is going to be JavaScript that is executed. So in all the drivers, that would be the way that you would ferry JavaScript over to the server. So in case of doing a MapReduce from PHP or Python or whatever language, you are going to write your JavaScript functions and send them. The driver is communicating to Mongo using the db eval command, and it's giving it the argument of your code. Whereas if you're using the JavaScript command line client, that itself is a JavaScript interpreter. So the same code that you would be running if I wanted, let's say I was writing my application code in JavaScript because I'm stupid, I would do that in the JavaScript.
If the PHP driver could do this evaluation in the middle, if this is a planned feature, if it is not possible.
No, based on the design, it sends JavaScript directly over. So usually you'll find with the drivers, you don't need to use, if you need to do queries, you need to do updates, there's actual driver things that will have the driver issue those database commands. So it's typically never efficient to send over JavaScript to do something you could otherwise do in the driver, unless you needed atomic locking or you had some operation that needed to be run that way. And then moving to MapReduce, which is also using JavaScript, how many people are not familiar with how MapReduce works? Okay, so basically you have a large set of data, and you have a function that scans over this data and emits any number of times, basically a key and then some arbitrary value for it. And on a single server, it's hard to grasp the concept, but the second step of the equation is the reduce query, which then takes all these emissions from scanning over the documents and compacts them down to a single result. So on a single server, the illustration isn't very grand, but when you have something like shards, you can dispatch your mapping and your reduce process and execute things in parallel across multiple multiple Mongo nodes. So basically you have your map function is JavaScript, your reduce function is JavaScript. And typically they're going to be small JavaScript functions. So although JavaScript locks, you're going to have the lock yielded frequently because you're executing small bits of JavaScript at a time. So in between your maps, which are typically reads, other things will be able to get in. And then in the process of how MapReduce works, it has to use incremental storage. So that's using write locks, because Mongo is internally collecting the data that you're mapping and processing it during the reduce phase. And there's other options around this, which are discussed in more detail in the documentation. But one of them is JS mode. For small data sets, you can skip all the write locks and just keep things in the JavaScript memory. And then finally, your ultimate output is going to be, depending on, sometimes you want to return it inline in a response directly to the driver. Other times you want your MapReduce results to go directly to a collection for later analysis. So that's also going to be a write lock. And depending how you output, the write lock could be held for longer. And then for indexing, there's basically two types of indexing available in Mongo. Foreground, which is going to block every database operation while you're creating your index. That's going to be the fastest way to create the index because it has control of the process. But if you're running a site with other downtime is not an option for you, you're going to probably want to use background indexing. It's going to be a little slower, but it is not going to block other operations. And this is just in the ensure index database command, there's a flag for background sure. And then the other benefit, which I personally like about this, during releases at Exercise and such, having to create indexes, was being able to watch how fast the index is being created opening a JavaScript client on the side and running the db current op command, which is basically like top in a Linux shell or a Mac. And one just caveat here is that if you have replication, when indexes are replicated to secondary nodes, by default, at least until 2.2, they're going to be using foreground mode. So your primary is going to be fine. You could do background indexing there, but this is something to be concerned about if you're targeting your reads to secondaries and you're doing indexes. And then in the slides, which will be available online, just link to the documentation, there's a manual way to go about this efficiently to maintain availability. So this is just an example of what db current op looks like. And in this example, I'm creating a foreground index in another window off screen. And this is basically all the statistics of the running operation. The important thing which I highlighted is that there's 3 steps, and you can basically see even just down to the percentage level how far Mongo is along in creating the index. And these are the three different steps as it constructs the B tree, which is the data object that indexes are represented as in Mongo. And then in background indexing, it looks a little bit different, but you also get the percentage. And so this was basically what I would be watching while we were doing a deploy and creating background indexes. And just what this will look like in PHP, a simple example of using the collection command to ensure an index and adding background sure. And separate from this is the safe option. And safe is basic, so by default, Mongo's database commands are usually dispatched asynchronously. So if you're inserting something and you had say a unique constraint on a username, you insert a user record with a duplicate name. If you're not using safe, you're not going to be aware of the error. Safe basically waits for the operation after it dispatches the operation, it then calls a method which blocks the driver to read the last error from Mongo. And so that's when you're inserting something, or if you're creating an index and you want to wait until the operation completes, you can add in the safe option. It was explained to me during employee training that a lot of the other drivers use safe by default. The JavaScript command line prompt uses safe in all its commands. So if you create an index there, even background, it's going to wait until that completes. That doesn't mean the database is blocking. It just means your client connection is blocking. But the PHP driver, its safe is not on by default. So just a quick benchmark of what this looks like. I inserted a whole bunch of documents in that format. And my benchmark was basically creating index by default. Creating index so by default is going to be foreground index without safe, so it's asynchronous. And then likewise for the second one. And you're going to see those return immediately because it's as fast as it could talk to Mongo. In the third and the fourth examples, I'm using waiting for the index generation to complete, but I'm doing it in the foreground. So it's going to take some time, but it's going to be a lot quicker than if I use safe and then also do it in the background, which is slower index creation. So these are just things to consider how safe interacts in general with your queries, and then also how background indexing works. In the ODM, due to some foresight by John Wage, safe is on by default when indexes are created. Background is not. So if you'd like to use background indexing, if you're running, say, a schema update on indexes when you do a Symfony deploy, you would want to add this to your model mapping. In this case, I was using annotations. And what that looks like on the command line, that would be the command that you'd probably run every time on a deploy in case you have different indexes that you want to get generated. So some indexing advice is, as much as possible, have one index serve multiple queries, because it's going to be not practical for you to have an index for every query in your application, unless you're having a really simple application. But in general, we could take advantage of compound key indexes, which are indexing 2 fields at a time, and allow those to service multiple queries. And it's really finding you're never going to get the most optimal thing for every query, but it's finding the cross-section of which queries can I most accommodate with an index. And then one other subject is multi-key indexes. So we have compound key, which is indexing two fields at once in a order. And then we have multi-key indexes, which are, so given that Mongo stores documents and it's JSON that you would throw into it, one of your fields might be an array. It's not going to be scalars like you would find in a relational database. So in a multi-key index, if you have an array field, Mongo will handle that for you and index all elements in the array, which makes it's something that can be taken advantage of when you're designing your schema for things like, say, tagging blog articles. You could just store an array of tags and have all those, have multiple values indexed for a particular document.
What happens if you put an index on an object?
So the question was, what happens if you put an index on an object? So Mongo doesn't go into the object and index its fields. It's essentially going to index the object's representation in binary. So essentially, if you index the field that has an object, to take full advantage of that index, you would want to query with that exact object as your criteria, and then it would be able to match. Unlike arrays, which it knows is just a sequence of elements, so even if it was a sequence of objects, the same rule would apply. Arrays are multi-key, otherwise it's indexing whatever it looks like in binary JSON. So in general, it's not efficient to create lots of single key indexes with no selectivity. So the goal of your index should be to partition your data as much as possible so that when the index is applied, there's much less documents to scan through. And then also mind your read-write ratio. So every index you have is another write. Every time you write to the database, those indexes need to be updated. So if you went and created dozens of indexes on a collection and are inserting one document, you might have to update a dozen different indexes, which are all going to be little writes. And in general, based on how querying works, you have various operators for searching collections in Mongo. Some of them are exists, which check if a field exists, not equal, and not in. And not in is for querying against arrays. So typically, these are not going to be efficient, not make efficient use of indexes because you're going to get a lot of false positives. So if you're checking if a field exists, it might have to scan the entire index because you don't have a value to query on. You're checking if a particular, just if a field exists in your document. On the other side, you have all, which is you would query against an array field and you would give it, say, 3 different values, and you want to return documents where all 3 of the values you provided are in that array. Or in, which is where you give it the reverse of that is where on a scalar field you would give it 3 different values and say, return me documents where this scalar is in my array of what I'm querying. And those on the counter side of the previous point, those can be slower because in in's case, you're only going to be able to use the index once for the first element. And so that might narrow it down, but then you're going to have to scan through the rest of the index for the other values that you need to check against. So in general, per query, Mongo is going to use 1 index. When in doubt, there's a tool built in to explain how your query is being executed by Mongo. Very similar to SQL's explain. Before we're going to dive into what explanations look like, but just the topic of memory usage. So this was something I pulled from previous production database. We'll leave it unnamed. And there was approximately 7.3 gigs of RAM on the system. This was an EC2 box. And the sum of our index size in Mongo was well over that. And the way this appeared in practice was that every now and then we would run a query and it would take, say, 10 or 15 seconds, or maybe 3 seconds. But if we're running index queries, we expect things to come back in milliseconds, and sometimes less than that. So the problem is if your indexes exceed your memory capacity, Mongo's not going to be able to store all those indexes in memory. And then your index queries, which should be fast, will have to get paged in from disk. And now you're talking about waiting for this other I/O mechanism of your operating system instead of just being able to query RAM. So basically, page faults and your disk access are going to be enemies. I mean, that's natural to happen when you're querying, when you're actually reading the data, but if you're using your index, you really don't want to have to experience that. And so to compensate, Mongo is going to shuffle indexes in and out of memory if it can't accommodate everything, based on what was most recently used. So just looking about how we can optimize a query by grepping the output of explanations. So here I just inserted 1,000,000 documents, which is no problem. And we have an incrementing field x and then a random field y. And I just did a quick count, and then I found the document where x was 5, and I explained what kind of cursor is being used. So basic cursor basically means that Mongo is not using any index. It's scanning through all 1,000,000 documents on disk. And as it reads them from disk, they're being shuffled into virtual memory. So if I ran this again the second time, it would be a little faster because that content would be in memory. But there's no index to take advantage here, and it takes about 300 milliseconds, which is perhaps arbitrary given we'll all have different machines, but with respect to the next benchmarks, it'll be more meaningful. And just to cover I hope this is readable, but the different fields here. So basic cursor means we scan the entire table, or was it index enabled? If it's index enabled, it would be a B-tree cursor. And then nscanned is the number of documents and index entries that we had to look through to solve this query. So there's no index, and we had to scan the table, so we had to scan all 1,000,000 documents. The number of scanned documents is just the document scan, which might be different or higher depending on what kind of query it is. But for now, there's no index. It's the same value. We matched one document. Query time was 300 milliseconds. The number of times the read lock yielded was 0. I had nothing else running at the time, so there was no need to yield. Chunk skips is related to sharding, which can be read up in the docs. And then was a multi-key index used? That's basically telling you, were you querying on array values? Just some extra feedback there. And then lastly, index only is, did the query and result come from just an index? So one of the benefits of creating your index is if you have small queries that say you just need to fetch a user in the last time they logged in, and you index the username and the last login time in a single index. You can query Mongo for just those 2 fields of a document, and if it can get all of that information from an index, there's no need to even scan the table data. So that's going to be probably the best way you can optimize queries that need to be very fast. And those are called different terminology, covered queries or index-only queries. Index bounds is the range in the index that we're searching. In this case, no index, so no bounds. So if I create a compound key index on the X field and the Y field, this is basically saying index the X field first, and then within X, I'd like to then index on the Y field. So the order is significant here. And now I'm going to find the same document where X is 5, and I'm just going to request the X and Y fields. Since the Mongo ID, the object ID, which Mongo creates for you, is usually always returned in the result unless you specifically exclude it. So I excluded it here so that we can see what an index-only query looks like. So here I just need the X and Y fields. It's already available in the index. Milliseconds was below the precision of the timing in Mongo, so it was effectively 0. And then it was an index-only query. And let's say I'm searching for the same, I'm searching for a document where X is 5 and where the Y value is greater than 0.5, which should, in this example, I do not know why I put X is 5 in here. It was probably bad copy, not thinking correctly, but it would, this is demonstrating searching for the X value and then using Y to do a sort. And the way this is going to use the cursor is query the index on X first, and then we can sort or do additional criteria filtering on the next field that comes next to the index. In hindsight, this was not a very good example, but it does show the way index bounds are, where we're looking at where X is between 5 and 5, so exactly 5. And then where Y is between those, the second value is essentially the largest JavaScript floating point. So just general advice with respect to indexes and then moving on to schemas is that don't be afraid of denormalization. Ideally, put the data in the form that you need to query it in, or that it's most usable to your application. Conserving storage space for most cases is not going to be, the benefits of doing efficient queries is going to far outweigh I'm storing a few extra fields in my document. I'm not being efficient with these extra 500 bytes. So whatever data is most frequently needed, make that more accessible. And then particularly in fields like counts and lengths, so if you have array fields in Mongo, say I have a user record and it has multiple addresses, and for whatever business reason I would like to keep a count of how many addresses that user has. It's not going to be efficient to essentially run a MapReduce query or something in aggregation to calculate the count in my query result. And Mongo, at best, is going to allow me to, in a direct query, I can just get array of addresses back. So in times where you need to query, on an index, or where query on a count field or sort on the length of a field or the number of elements in an array, it's usually best to denormalize that field and then just keep that value in sync with your array. And you have atomic operators. When updating, you can directly set a field atomically instead of writing out the entire document, or you can just increment a field. So this can be maintained very easily in your application. In general, this is a slight departure from, I understand how Doctrine works, but for tracking references to other documents, which is foreign keys in SQL. So typically, I think a lot of Mongo users that aren't using object document mappers and aren't directly tying things to their model typically don't have as many references. Whereas I'm looking at OpenSky's application or Exercise's application, we created these PHP objects directly related to our business requirements because we had the freedom to store PHP models directly, map them directly to Mongo documents. And so we have some things are denormalized, but we have a lot of references. And looking at the 10gens customers, this is much higher with companies that are using ODMs than the companies that use Mongo directly, just without that layer of abstraction. So the two things here, there's two ways to do database references, and one which is which Doctrine uses by default is dbrefs, and these are basically little objects that contain the ID of the document you reference, the collection name for it, and the database that it's in. The database name is optional, but Doctrine sets it anyway. And then recently, we added support for just references by just having an object ID stored in a field. And so right off the bat, you're not storing the if you're always referencing, if user is always referencing in an address object, you don't need to store collection address in every reference. We just need to store the address object ID. And since we're using a model, it's only ever going to refer to that. So this can make your storage more efficient. And then another issue that comes up is especially when going from translating how we think in SQL to how we think in Mongo. When there's pagination on, I would assume even I don't know if it's the KMP bundle or something else that does pagination, the main bundle for this. Maybe it's Pager Fanta. It uses skip and limit to do pagination, and it's basically a complete one-to-one relationship to how it would work in SQL. In Mongo, this is quite inefficient because skipping entails walking through all the documents in the index, or if you're not using an index, walking through everything on disk. It's not immediately jumping to the location, the offset where it might exist in a table like it would in SQL. So the 10gen solution for this is to use range queries, and this limits you to having next and previous links unless you add in some extra logic. But using range queries allows the index to more efficiently get to the page that you're attempting to go at. So if you're using skipping, you're going to find the first couple of pages are efficient, but as you go on, and this comes up in Exercise where they have, say you have SEO index content and it goes up to hundreds or more pages. and you're getting crawled, as those later pages are loading, your skipping increases, and every page load you're doing more processing in Mongo. Your queries are going to get slower. And I just linked to a good Stack Overflow response discussing this. And also the B trees, which are the index representation of Mongo, don't track counts for nodes and branches. And I kind of learned this the hard way at exercise. I was just assuming it's an index. It should know exactly how many there are of a certain value. So if you're filtering on a count query, it's going to, at best, have to walk through the index and count those values. And if it's in memory, it's no problem. But in our case, where we had indexes swapping in and out of RAM, every now and then we did a count, which we think, oh, it's a count. It's just returning the number of things. It should be always fast. It would have to walk the index, and it could have other repercussions there. But if you are counting just how many things are in a collection, you can get that in constant time. And the way this manifests itself is if you frequently find yourself counting the number of enabled users in your database, and you happen to index the enabled field, which probably has low selectivity because most of your users are enabled, that's not going to be efficient. Alternatives would be to either cache that value elsewhere or not store disabled users elsewhere out of the collection. Another point is when this comes up a lot doing migration scripts, which we did through numerous phases of OpenSky's business. When you run queries, there's a mode called snapshotting, which is not activated by default, but it ensures that the documents are only returned once. So when you're doing a find across Mongo and it's going to be searching through all the collection data on disk, if you're updating documents or changing the size naturally by adding enough fields where it doesn't fit to where it was originally stored on disk, it has to relocate it. There's no protection without snapshotting that would say I might see that document again later, or it might relocate something and I might miss a document later. So snapshotting ensures that when I'm doing a query and I'm updating to the same collection, I see exactly what was there at the beginning of when I issued the query. So very important for migrations. There's no guarantee if you're inserting and deleting documents for new documents or documents you're taking out. But for the snapshot is basically just for updating and having things that you expected to be there being moved. So the insert and deleted, don't be scared of that. So a little bit away, Doctrine works with DB references and discriminators and Mongo command line client. So I'm just inserting Bob into my users collection, and I'm giving him an address the same way that Doctrine might use a discriminator field, a discriminated reference. And basically, discriminators in Doctrine are, we have multiple models, say a shipping address, a billing address, a work address. We want to store them in the same collection. When I fetch these documents out of Mongo, I want Doctrine to look at a type field and hydrate it into the appropriate object that I expect it to be in. So that's already happening at the collection level, but then also when we refer to a discriminated object on the reference, Doctrine is also going to store this extra discriminator field. In this case, I'm calling it type. And that's going to hint at how that reference should be hydrated. And particularly this is necessary because Doctrine is going to proxy that object until you actually read something from it, but it needs to make the proxy of the appropriate model. So if I just find my user back from the database and I just ask for the address, I see the address return as this DB ref object. And it's essentially hiding these extra fields that the JavaScript console thinks I don't care about. And this was bit us very hard in in migrating between two exercise releases because we had to basically add discrimination to a collection that we had, which is basically our activity stream. And we needed to add some commentable activities and still maintain the ones that were not commentable, that were just feed items. And in migrating this, I was doing reconnaissance on what the data looked like using the Mongo shell, thinking, oh, I could trust the Mongo shell. And had no idea that Doctrine ever stored discriminators on reference fields. So after we ran the migration, that was a really bad Friday night and Saturday all day. And we basically had all these references to these ACT objects scattered throughout other models in our application, and they had no knowledge of how the object should be returned. So everything that was referencing what should be a commentable activity item was giving back a normal, a non-commentable activity item. This is just something to be aware of. I felt compelled to share it. If it only helps one person, I consider it worth it. And basically, the fields are really not, they're technically not hidden because you can access them directly. But by default, they just won't be shown. And this is exactly what I just went over. So just a case study of refactoring Ornicar message bundle. So this was something that Exercise was using, and it's basically the same concept of Facebook messages. You have a message between yourself and n number of other users on the website. And there's basically message and thread documents. Threads hold multiple messages. They're not embedded, though. They're separate. And then on that, we had these fields, which were actually hash types in ODM. In Mongo, this is just going to be an object with dynamic keys. But ODM is going to call this a hash because otherwise an object in Mongo usually relates to a separate class or a separate model in ODM. So hash type for dynamic keys, and we basically had these maps of user IDs as a string to a Boolean value or to a date value. And we had four such fields. And this is what the query looked like when I needed to get the number of unread messages by a participant. So we had to construct this dynamic field name and check where it equals false. And we counted this. So does anyone see a problem why this might not be a good idea, this dynamic field name? So this is going to be incredibly difficult to index because as Benjamin asked before, how does Mongo index objects? It'll index the entire object, but it's not going to index individual dynamic fields within the object unless we specifically create those indexes. So can we index is read by participant? No, the entire object would be indexed, and it's really ridiculous. We can't anticipate searching that because we don't know all the participants. And we can index all the keys, but that's 5 indexes just for this one, for each user would need its own index. And so instead, we can do one multi-key index. And this involves structuring our data around a little bit differently. But now this allows us to use, just query that multi-key, take advantage of the multi-key index and just query that array and see where our participant happens to be in this array. And even though this is a quality, Mongo isn't comparing arrays to the ID. It knows that you're dealing with an array and you're giving it a scalar. It's going to check if that scalar exists inside the array. So I'm going to blaze through MapReduce here. So I have this schema of articles without content. We just have the author and tags for the articles. And, sorry, to generate a report for each unique tag in the system, the authors that are affiliated with this, there's this hairy JavaScript that we have to write. And basically, we're going through all the tags in every document, and we're doing emissions for every tag, and then the author for that. And then we reduce it. That's essentially the counting. And so the result is going to look something like this, where we have our tag, and then we have everything that I reduced down to, where I joined all the arrays that were emitted. Is there an easier way to do this? Because this isn't really maintainable. And this is a simple example. This is going to get much worse. So this is where we have aggregation framework, which is currently in Mongo 2.1, unstable if you want to play with that and develop. But it's going to be in 2.2 when it's released soon. And it basically has two concepts, or one concept. There's a pipeline of operations. This is very much like a Unix shell pipe, where strings are piping through different operations. So now instead of processing strings, you're processing streams of documents. And you do these transformations in sequence. And the main benefit here is there's no JavaScript. So there's no concurrency issues. You're dealing with, you're basically expressing your aggregation exactly as you would queries in a JSON structure. And you invoke this on collections. You could do filtering with a pipeline operation, which is match. And this is also compatible with sharding. And basically, the different operations available are projection for altering the content. You can match, limit, skip, which is different than query, than skipping on a cursor. Unwind on array values, essentially, if I encounter a document with 5 array values, I want to multiplex and now add that document 5 times to the stream, 1 for each array value. So this lets us essentially unwind the array and process them in the same pipeline. And we have grouping and sorting. And then for expressions, you have a lot of things that you would normally expect for string manipulation. A huge plus is date handling. So previously in Mongo queries, there's no way to, you have these timestamp objects. Say you want to get the month name out of the date. There was no way to do that in Mongo without using JavaScript and interpreting the date as an object and returning a string. So you have date handling where you can very efficiently pull the month out of a string and replace that field in your pipeline. The benefit of this, it's all running in C++, much faster than JavaScript. And essentially, all that JavaScript was condensed down to this simple pipeline where I want to deal with author and tag fields. I want to operate on each tag field, and now I'm consolidating by adding each author to a set. And this is, can't be explained in 10 seconds, but it's incredibly powerful. And it's something that definitely, going through the docs, it should be easier to pick up, certainly easier to wrap your head around than MapReduce. So very lastly, in the final minute before I kick off, just benchmarking Doctrine ODM and explaining, maybe this was most relevant to people attending, when to use ODM, when not to use ODM. So I did a benchmark with persistent flush using the query builder, using just the Doctrine class to work on the collection, and then the Mongo collection driver class, which is as close as we can get to the raw driver. And I want to track the insertion time and the memory usage. So I know it's notorious that ODM has memory leak issues. A lot of these are related to, some of them are related to how PHP has circular references, and those are getting better as new versions, but there's still, if you scour the issues, there's still memory leak issues. So using ODM flush to insert 100,000 documents, it took about 50 seconds, used about 600 megs of RAM, and after I was done and I cleared the document manager, I still was using 150 megs of memory. And as I drop down, stop using flush, and I go to just using the execute querying, and there's no object tracking, I'm down to 3.6 megs of RAM, and used just for that operation. And at the end, there was 8 megabytes completely allocated to PHP. And this gets progressively better as we go down to the driver. So basically here is when you're doing large-scale migrations, this is a time where you stop using persistent flush, stop using your object model, and there's points where you go down to start working with your model as arrays in PHP using the raw driver. And a migration that might take days to complete otherwise, or many, many hours, you're doing in timestamp of minutes or seconds. And then the last 3 slides are just to discuss Mongo monitoring service. So this is a free software solution that 10gen hosts. You install a little Python script in your Mongo cluster. It sends pings over to 10gen, basically non-specific statistics about your server, your op counters, your loads, things like that. You can plug it in with Munin to also get your hard drive and processor time. It's a free service, and basically you have an interface such as this and these charts. And this really helps when you submit a support ticket, and the engineer assigned to it at 10gen has to go through and kind of guess what your issue was. So if you want to follow up, there's a lot more content than I could explain here. Next week in Paris, there's a MongoDB conference, and then the following week, there's one in UK, in London. So we're out of time, but if there's any questions, I'll be standing up here. I brought not enough of these because I had to check my luggage. A little MongoDB book, and I have about 16 of those, and about 20 reference cards. So if you are actually going to need this, or you want to share it with your coworkers and you can't deal with just going to documentation, it's good plain reading or anything like that. But thank you for your time.